of the trefoil is tricolorable. In particular, take any tricolorable projection, mess it up by Reidemeister moves, the result's still tricolorable. So if you think about it, since all diagrams of the same knot are related by Reidemeister moves, it means either all the diagrams of a knot are tricolorable or none are. So if you wonder, whether some diagram of say I give you a complicated diagram and I tell you it's of the unknot and someone's like, tricolor it, you'd be like, no way, because I know one diagram of the unknot is not tricolorable. That means none of them are. So in other words, here's a corollary. Either every projection of a knot is tricolorable. Let's say of a knot, say K. Let's be a little precise. It's tricolorable. Or no projection of K is tricolorable. So it's like it's all or nothing. Okay, so I guess if you believe this theorem, what can you conclude? Is the trefoil the same? If I draw that like a picture of the trefoil that I've been drawing, can I somehow simplify that picture by Reidemeister moves to get this?
No.
Sean says no, right? Because every sequence will preserve the property of being tricolorable, and if this is tricolorable and this ain't, then there's no such sequence. So if there's no such sequence, this really means this can't be unknotted by Reidemeister's theorem. So this is actually, if we believe this theorem, we now have a new corollary, which I'll explain. I guess I'll also explain a little bit more next time about this, but I hope it's obvious. The corollary is the trefoil is different from the unknot. So we've now, if you believe this result that we deduced this from, then we found a new knot other than the unknot. So, but of course we can't, this is like, it seems laborious to get to this stage, but there was a lot of sort of preliminary stuff that, just basic for starters. So we only have a few minutes left, so rather than start on the proof, I guess what I'll say two important things. One is, we're going to prove this next time. I think we have just enough time. But look, you can read the proof in the book. It leaves the last part as an exercise, which I'll do in class. But you might also want to think about it yourself. Like, how would you try to prove something like that? Like, you have to prove that if this is part of a diagram that's tricolorable, so say you tricolored it, and say this part's colored white, but you don't know what the rest of it looks like. You just know there's more than one color. And you modify it by adding a loop, that's the first move. How do you tricolor the new thing? Well, you can't see really what's going on outside, so you should just say, well, I'll try to color that part the same. But if you think about what that does, you'll say, well, this might connect up to something here that's doing, who knows what's going on. This color has to sort of stay the same. This color has to stay the same. Here it's coming in, and you're like, oh, it forces this to just remain the same color. Does that still work? And think hard, or just for some of you it was a little obvious. You might say, oh, this satisfies the condition at the crossing if I make everything the same color. The only thing I can be concerned about is to use more than one color thing, because the coloring outside is the same. But I'm already using more than one color outside the dashed area. So the other important announcement I want to make is looking at this problem set. I guess number 6, 7, really to do the last step, you kind of need to have gone through the proof I wanted to do in class to kind of get a fair exercise. And number 6, unfortunately, I didn't explain what I want. So just do 1 through 5. So I'll announce it over email too, but just do 1 through 5 for Monday. If you've been thinking about 6 and 7, that's great. That'll be on the next assignment, so it's not like I'm gonna throw it away. So 6 and 7 for the next assignment. You have a copy of this.